This is a video demonstration on the principle of diffraction. And what this experiment or phenomenon shows is that light must be a wave of some kind. So what you'll see in front of you is two lasers. One on top is a red laser and the one on the bottom is a green laser. I think from the video it's a little bit glary, but hopefully you get the idea. So the idea with light is both of these lasers are traveling at the same speed of c, but they have a different wavelength and a different frequency, but they both travel at the same speed. So what we're going to do is we're going to put a diffraction grating, the same diffraction grating on both, and what you'll see is that you get what's called the diffraction pattern. And if we can line it up a little bit better, perfect. What you should notice is that given the red light is around 700 nanometers and green light is around 550 nanometers, red light has a longer wavelength. So when it diffracts through these gratings, what happens is that the spaces between the dots should be bigger for the bigger wavelength. So the bigger the wavelength, the bigger the spacing between the dots. This is a video demonstration that illustrates the wavelength nature of light. So this is based on one of the most famous experiments ever. It's called the double slit experiment. And what it shows is that light diffracts, which means it'll bend around corners and through holes, unlike particles. And so this showed that light definitely had to have wave-like properties. So what you'll see in front of you on the screen is a bunch of concentric circles, and they're actually two transparencies that have these circles. So what we're going to do is we're just going to move them apart a little bit. And perfect. So what you'll notice here is that in the middle, it's very bright, and then you'll see a dark band, and then a light band, and a dark band. So this is the same thing that happens when we looked at the light that was diffracting, where there is constructive interference coming from both slits. You get two crests meeting or two troughs, but they're in phase, so you get a lot of energy there. And so if it was like boats on water, the boats would be going violently up and down, where you see the bright lines. Where you see the dark lines is where you see destructive interference. And so literally the waves cancel each other out there, and the boats would just be flat on the water. So they've done this experiment with sound, they've done it with light, they've done it with electrons, and all of these things have wave-like nature. Just want to change the distance between the slits D here. So distance D is the distance between the two sources. So if we make that a little bit smaller, and we bring them closer together, what you'll notice is that there's an inverse relationship. The smaller D is, the bigger the distance between the maximum and minimums are. This is a video demonstration that This is a video demonstration showing constructive and destructive interference. So what you'll see in front of you is a plate, and that plate is attached to a big pulsing vibrator underneath that goes up and down vertically. And what it's going to do is it's going to push up and down on the center of the plate, but because the plate is extended out, there's going to be kind of a wobble to it. So it's kind of a neat thing to show what a node and an antinode is. So what we're going to do is we're going to dump some sand on it, on the plate, and yeah, we'll maybe turn it on. It takes a little while to get going. And we'll just dump some sand in the middle. Perfect. And we'll wait till that gets going a little bit. All right. So what's happening is the you see kind of a cool pattern there. What you'll see is where the sand is just sitting there. That would be called a node. So that would be destructive interference. Where you see the sand jumping all over the place, that's where high energy is. So that's constructive interference. So it just shows nodes and antinodes. If we change the frequency a little bit, it's a pretty cool pattern that's happening here. Whoa. And so what you'll see is where the sand kind of no matter how it's vibrating. The sand would be defined as a node because it's not changing, or there's very low energy. So that would be a dark spot for the double slit experiment for light, and a bright spot would be where you see no sand. There's violent energy